Okay, so section 5.4 is on graphing polynomials, and there's three things we want to talk about: how to graph them, what is something called the location principle, and then the extreme points on the graph. The plural of extremes, extrema, so like the maximum and minimum points on the graph, and how many times can we figure out how many times the graph is going to turn, and that's called a turning point. Okay, so first of all, graphing a polynomial, there's no easy way to do this by hand. So really the easiest way to do it until you learn calculus, when you start to know better about the shape of a graph and something called inflection points. Until you know that, the best thing is just to make a table of values. And for something messy like this, you can see this table of values has all these decimals in. For something messy like this, I would just put that in a calculator and see what the table gives you. So we'll do that right now. F of x, by the way, that's another name for y. So I'm going to put into the calculator negative x to the fourth. So you go to y equals negative. Notice that the negative key is on the bottom right there. So negative x, that arrow key is the exponent there, the one that just lit up in red. Negative x to the fourth. And then the rest of it is plus x cubed. So plus x cubed plus, by the way, you need, when you fill in the exponent, you need to hit the arrow to come down. So now it's blinking in a bigger motion there, so I can see I'm not stuck up in the exponent. 3x squared, and then plus 2x. And we can get the graph of this by going to zoom standard. If that doesn't give us a good picture, it gives us a reasonable picture. If it doesn't, you can go down to zoom and then zoom fit and press enter. Actually, zoom standard in that case was a better picture, so we'll do that. Okay, and then if you want to see where the table is, you go to second, and then right above the graph, there's a little, you can see it there in blue, it says second table. And this gives you a huge table. Now my table's not, these are kind of weird numbers, so if your numbers are not showing up like you want, you go to second table set, that's above window. You tell it where you want to start. So let's say we want to start it at just a random number. Let's do negative 10. And this second one, this triangle right here, then this TBL, that means delta table. That means how much do you want the numbers to increase by in the table each time. I want them to go up by 1. These other ones, when it says auto, if it says ask, that will allow you to plug numbers into the table, but we just want to have them do it automatically, so we'll put auto. We'll go back to second table, and now you can see what all these values are for the polynomial. We can scroll down, and this tells you, for example, the 0.00 is on this graph, the 0.15, the 0.28, and so on. That's how you graph using the calculator. Okay, what does the location principle mean? The location principle means that if you cross the axis, if you know, like let's go back to this table, I know that there's a 0 on this polynomial between x equals negative 1 and x equals 0. Okay, I also know there's a 0 between x equals 2 and x equals 3. How do I know that? Well, here's an example. It might seem kind of strange, but just go with it. If you're driving through Texas, let's say you're in the back seat of a car, you're driving through the state of Texas, and then you wake up a couple hours later, all of a sudden you're in Mexico. What happened while you're asleep? And the answer is you must have crossed the border. So if you look at this y column that's highlighted in black, notice that I'm at 0, I'm at positive 5, positive 8, and then suddenly I'm in the negative. So if I cross from positive 8 to negative 21, what must have happened? I must have crossed 0. And so the location principle says we can locate the fact that there's a 0 somewhere between 2 and 3. I don't know the exact value, but I know that because I crossed from positive 8 to negative 21, I must have done that somewhere between 2 and 3. So there must be a 0 somewhere between 2 and 3. That's what the location principle says. And this is just another way of saying it. If you look at this, let me change the color here for a sec. If you look at this graph right here, I know that there's a 0 right there. So I know somewhere between that x value, somewhere between, let me highlight a little bit better so we can see it, somewhere between this x value and that x value, there must be a 0, even if I don't know exactly what it is. Okay, this one says determine values of x between which the 0 is located. So we can do the same thing. We can take this function and plug it into the calculator. Oops, that's a +1 there. And then we'll look at our table and see where did a 0 have to have occurred. So we'll do that right now. So let's plug in x cubed minus 4x squared. Go back to y equals, clear it. X cubed. And then I'll press arrow to come down from there. Minus 4x squared. And then the rest of it was plus 3x plus 1. Okay, so now I have it, so I'm going to go to second table, and you can see this crosses from negative numbers to positive numbers between -1 and 0. So I know there's a 0 somewhere between -1 and 0. And then it crosses again between, right here from 1 to -1 it crosses, so I know there's another 0 between 1 and 2. So let's test that theory. I know there's a 0 between 1 and 2, so let's go to zoom standard. I want to look for the 0, so right about here between 1 and 2, so let's calculate it. Second calc, 0. And then I'm going to look for this 0 that we know over here is between 1 and 2. So I'm on the left of that 0 right now. Oops, this one. On the left of that 0, press enter. Then I go to the right of it, press enter. And then press enter again. And we said there's a 0 between 1 and 2, and you can see that it's at 1.44. That's between 1 and 2. By the way, because this is being raised to the third power, you can see it has, let me zoom in a little bit so you can see it better. Zoom in. You can see that has one 0 on the left, it has another 0 right where my cursor is, and then it has another 0 over here. It has 3 zeros, that's because it's raised to the third power. And in section 5.3 we said an odd degree, like to the third power, is going to have an odd number of zeros. So that checks out. Okay, this second thing, or really one of the last things we want to talk about, is something called the extreme points on the graph. And this is a good picture right here. The extreme points on the graph, so notice this right here looks like it's an odd degree polynomial because it has an odd number of zeros. There's a 0 right there. Extreme points mean like hills and valleys. So this right here is like the top of a hill, and this right here is like the bottom of a valley. Okay, the reason that these are called relative, that you can see from reading that, relative maximum and relative minimum, is because this point, let me put it in yellow, this point right here, that's not the highest point on the graph. Like this arrow right here keeps going up even higher. So all of these points right here are higher than that yellow point. It's called a relative max because it's relatively speaking higher than everything else around it. So these points in green right here, this point and this point, are lower than that yellow point. Relatively speaking, it's a maximum. It's like a hill compared to what's around it, even though it's not the highest point on the graph. Okay, same thing down here. This green point right here, relatively to the other points around it, is a minimum point. But it's not the lowest part of the graph because way down here, all these points right here are lower than that green point. So the green point is a relative min. Okay, we also talked about this in section 5.3, something called turning points. So I will put the turning points in black here. Okay. The turning points are these minimums. So right here the graph turns from going down to suddenly going up. Right here at the max it turns from going up to suddenly going down. So that has 2 turning points. And what we can, so I'll say 2 turning points. What we can tell from this, or what we know about turning points, is that the degree of a graph, the possible number of turning points it can have, is always 1 less than its degree. So for example, this graph right here could have at most 2 turning points, x to the third. X to the fourth could have at most 3 turning points. Okay, x to the 100th power could at most have 99 turning points. It doesn't have to have that many. That's the maximum that it could have. For example, if you had a graph with 100 turning points, it couldn't be x to the 100th, because x to the 100th can only have at most 99. Okay, so let's graph this right here. Just to save us some time, when you fill in the table like we were doing before, you get those points right here. So these would be easiest to graph on a calculator. So let's graph that: x cubed minus 4x squared minus 2x plus 3. We already have most of this in here, so this should be a minus 2x. Delete this, and then minus 3. Oops. Deleted that whole thing by accident. So x cubed, and then we have minus 4x squared minus 2x, and then what was the last part? Plus 3. Okay, then we'll go to zoom standard, and we get a graph like that. Well, again, we know that this is to the third power, so it should be having at most 2 turning points, and it does. You can see one is on the top, one is a little bit lower. The question is, estimate the x-coordinates at which the relative max and min occur. So there's an easy way to find that. Let's go to second calc, and let's find the max. So I'm right, if you see from that graph, I'm right near the top. I'm going to the left of that. Let me go to the right of that, press enter. Enter again. The maximum is at x equals negative 0.23, and the y value at that point is 3.23. So let's fix the graph. Let's go to zoom fit. That's actually, I think we had a better graph before. Zoom standard was better. Okay, and then this min is a little bit downward, so I'm going to zoom out just a little bit so I can see this better. So I'm going to go down here, zoom out, and nope, that was not good either. Sometimes you have to play around with this. Okay, let's do second calc and let's find the minimum this time, which is a little bit off the page. Minimum is down here. I'm to the left of it, then I'm to the right of it. Let me go down a little bit. The minimum occurs at x equals 2.89, and the y value at that point is y equals negative 12. If you want to see a better picture of that, I'm going to go down here and hit zoom in. You got to go below a little bit, and there's the minimum right there. You can see it's about x equals 2.8 something or 2.9. Okay. By the way, this box right here, Desmos, that's a good website. If you type that in, it has a nice graphing calculator. It's a little bit easier to use. You can feel free to use that as well. Okay. So that's just a kind of a last picture of what the graph looks like. When they talk about graphs increasing or decreasing, increasing means as you're going from left to right, you're going up. So the graph is increasing on this yellow line right here. It's also increasing right here. But in between them on this red line, the graph is going down, you're decreasing. Okay, so that's what they mean by f of x increasing or decreasing. Okay, last one is, a lot of real-world equations are modeled by polynomials. So this is an equation that shows how many people annually pay money for movie tickets. It has that big function right there. X stands for the number of years since 1926. F of x or y is the number of people going to the movie. So when you put this in a calculator, when you put this whole thing in a calculator, graph it, you get this table right here. Describe the turning points of the graph. Well, it's raised to the 4th power, so it could have at most 3 turning points. There's 1, there's 2, there's 3 on that picture. Its end behavior. Well, the end behavior is a 4th degree. So remember, 4th degree or any even number degree behaves like a parabola, but because that's negative, it's going to behave like an upside down parabola. So that means as x goes to positive infinity, f of x, the function, is going to go downwards to negative infinity. You can see that right here. This thing keeps going down. And then as x goes to negative infinity, which is over here, that graph is also going down. So f of x is also going to negative infinity. That's the end behavior. C says, what trends in movie admissions does the graph suggest? It suggests that movie admissions are going down, because you can see as we're getting further from 1926, this line is decreasing. There's a little stoppage point there. It goes up slightly, but then it starts decreasing. Is it reasonable that the trend will continue indefinitely? Well, no, because you're not going to, for example, this arrow would go down to infinity. You can't have a negative amount of people going into a movie, so that it's not like nobody's going to go to movies. It's probably going to start to bottom out somewhere, and that's basically what that says. It's not reasonable for a graph to go down forever when it comes to a real-world situation. So that's section 5.4 on graphing polynomials.